All right, let's get started here. This is the fluids in motion or forces in fluids practice worksheet, and we're just going to go through every single problem one at a time. And number one, right away, it's a typo in there, and I think Melania found this one. So first of all, it's a pressure problem. So right away, you know you're going to use the pressure formula, and the pressure formula is pressure equals force over area. So how much force are you applying to a given area? So we're talking about a horse hoof applying a force to an area. Now, I told you it's 0.25 meters per second squared. That's a unit of acceleration. It's a mistake. It's supposed to be 0.25 meters squared. So yeah, that's my bad. But if you plug that in, where I give you everything but the pressure, so the pressure is still an unknown, I give you the force, which is 1,000 newtons. That's an awesome N. So 1,000 newtons. And the area here, not the acceleration, but the area is 0.25 meters squared, which means it's 0.25 meters by 0.25 meters. Because it's an area, and areas are all squared by their nature. So this one's pretty easy. It's just a little division problem for at least the numerical portion of it. So you're going to go with 1,000 and you're going to divide that by 0.25. So the number should be, again, the numerical portion should be 4,000. But now when it comes time to the unit, what is going to be the actual unit? Well, in this particular case, you can go with two ways. You can either figure out the unit itself, but in this case it's just newtons per meter squared. If you just look at the math, that's what it works out to, and you can leave it as that. Or you can write 4,000 pascals, because that's the combination, the combo unit. Because remember, scientists are lazy and newtons per meter squared is hard, so you can write 4,000 PA. Both are fine. So both of those would be a fine answer for this particular problem. Unless I did my math wrong, and I don't think I did. That's number one. Let's go with number two. So number two, we have it's the same type of problem, but in this case we're looking for the area. So it's again a pressure problem, so we're going to do the formula. Pressure is force over area, and in this case I'm giving you the pressure, so it's 500 pascals. I'm also giving you let's see, what am I giving you? The force, which is in this case 500 newtons. And I'm just looking for the area. So you just simply solve for A. That's all it is. So I'm going to flip everything essentially. And I'm going to end up with 1 over 500 pascals equals to, and there's lots of ways of doing it. You could also cross multiply. Cross multiplication probably be best. But in this particular case, to find A now, I just need to multiply both sides by 500 newtons. So in this case, that's gone, and in this case, the numbers disappear. And I'm left with area is 1 Newton, so 1 Newton over Pascal. So the answer is not just 1, because you need the units. Now, you probably figured out that the units in this case are going to be meters squared, but how do we do this? Well, if you go back and do the math, this is how it works out. So you know that pascals are newtons over meters squared. And this is all over 1 Newton, right? Or just a Newton. You say it's over just a Newton. So the way this works out is that the newtons cancel each other out. And because the meters all the way at the bottom, it jumps to the numerator here. So the answer is just 1 meter square. That's all there is to it. A bit of a convoluted math there. And again, if you really want to, if that's a little confusing, again, this whole thing, you can say newtons divided by newtons over meters squared. Change that to a multiplication, newtons times meters squared over newtons, and then you can see they cancel out, or you're just left with the meters squared. But again, this is math, not doing math here. You should have learned that in algebra. Moving on to number 3. Number 3 is, what is the net force if you are pulling a dog leash with 250 newtons and the dog is pulling the leash in the opposite direction with 280 newtons? I think we did a problem like this before. This is a net force problem, so that's fine, whatever, not a problem. I think this is from the last lesson though. But so you have a dog there, and you know it's a dog, so dog with like ears. Dog or cat, whatever, don't judge me. And it's got a leash, it's got a nice little leash here. Let's make it red. And you're pulling on this leash with a force of 250 newtons. And the dog is pulling on the leash. So the dog is like no, or with a force of 280 newtons. So what's the net force? Well, it's 30 newtons because 280 minus 250. So the net force is going to be 30 newtons in the dog's direction. So the dog is, in this case, more powerful than you. So the dog is slowly going to move in the direction that it wants to go. Yep, that's it. That's the answer to that problem from, I think, the last lesson. I'll move it on. Now we're going to be calculating the weight of an object if it has a mass of 150 kilograms. This is also from the last lesson. Interesting. Fine, whatever. It's fine. It's fine. A bit of a review, not a problem. So we're looking at the weight of an object. I think it's from the last lesson. I'm not sure, maybe not. So the weight of the object, W. If it has a mass of 150 kilograms, well, so acceleration from gravity times the mass of the object. That's all that is. So in this case, and I'm assuming we're talking about Earth here because I didn't specify. So if I don't specify, we're talking about Earth here. So the weight is going to be 9.8 meters per second squared times 150 kilograms. Well, in this particular case, all you need to do is take some math. 9.8 times 150. That's going to give you a nice 1,470. And you can go ahead and do the math, but if you remember, the kilograms times meters all over seconds squared, that's also the same thing as a newton. Also a newton. So either one of these two units would work. So either you write this or this, but not both. So that was number 4. Let's take a look at number 5. Seems like almost the same type of problem. So the mass here, so we're going to have to find the mass. So it's a weight problem again. So weight is acceleration from gravity. In this case, I think it's Earth again. Times mass, and I'm going to give you the weight here. So it's 600 newtons equals, so we know it's 9.8 meters per second on Earth times mass. So in this case, again, it's a simple math problem. You divide both sides by 9.8, so 600 divided by 9.8, which is going to be roughly, it's 61.2. So 61.2, and the unit is going to be kilograms. Now again, that's because I know that, but how do you know that? Well, if you take newtons, and again, I'm just going to do it over here, newtons, and divide that by meters, divide that by seconds squared. The seconds squared is going to pop right up top here. So it's going to be newtons times seconds squared all over meters. No, that's wrong. You know what, I take that back. So it becomes, I'm just going to do it right over here. It's newtons divided by meters per second squared, which is the same as newtons times seconds squared over meters. And then if you remember, newtons is kilograms times meters all over seconds squared times seconds squared over meters. So the second squared cancel out, the meters cancel out, all you're left with is kilograms. So again, you can either go with this because you remember that the mass unit in this formula is kilograms, or you can do the math. Both are fine by me. So that's number 5. I'm going to move on to number 6 now. Erase all, please. Okay. Number 6. So you have a rock with a volume of, okay, a volume problem, cool. Or a density problem, huh? So the formula for density is mass over volume, m over v. So essentially it's how much mass can you fit in a certain volume. So that's a pretty simple formula. And I'm gonna give you here, let's see here, the volume, and I'm gonna give you here the mass, and I'm looking for the density. Okay, perfect, that's an easy one. So density is volume, which in this case is 15 centimeters cubed. And if you remember to the very start of the year, I told you that volume can be measured in the metrics as both liters as well as meters cubed. So you can do volumes as both a fluid volume, how much fluid something holds, but also you can do it by measurements, by multiplying the length, width times height. So that also gives you the volume of an object. So if you are, for example, calculating the volume of a room, how much space a room takes up, you could either, obviously calculate how much fluid it'll hold, or you can do, length, width, height of the walls. A lot of times it's easier, especially if the room is not weirdly shaped. Back on topic, and you have 45 grams. So that's a simple problem. So density in this particular case is going to be 45 divided by 15. That's 3 grams per centimeters cubed. Then you can leave it at that. Now, ideally you want to convert it to kilograms over meters cubed, but it's fine. This is fine. We can live with this. Number 7. So you have a different rock with a volume of 30 centimeters and a mass of 60 grams. What is the density? Okay, more of the same. Cool. So again, we're looking for density. In this case, it's 30 grams and the mass is 60. Bad? No, Mr. B, you're bad. 30 centimeters cubed. That's a grade 2. It's also grade 2. There we go. And that one's going to be 1/2 grams over centimeters. Okay, that looks weird. I shouldn't do that. So it's 0.5 grams over centimeters cubed. It's going to be like a fraction over a fraction. You could do that. You could say just 1/2 grams over centimeters cubed. That works too. Yeah, whatever. Yeah, that's fine. So that's number 7. Let's do number 8. In the above two examples, which rock is heavier, which is less dense? Well, that's pretty easy. The second rock is heavier because it's 60 grams, but it's way bigger. It has twice the volume. So just because it's heavier, it's not more dense. So the first rock, and number 6, is more dense by actually quite a bit. Then the... Wait a second, Mr. B, you are not good at this. So, number 7, we're going to go back to that one. I put the units in the wrong place. Grumble, 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 grumble. So did I? It's 30. Yeah, so it's 60 grams. Wow, Mr. B, 30 centimeters squared. That looked weird. So it's actually not a half. It's a bad Mr. B, bad Mr. B. It's actually 2 grams per centimeter cube squared. All right, that's the answer for number 7. So number 8. Same thing still. The second rock in number 7 is heavier, but the first rock in number 6 is more dense. And apparently I am also kind of dense because I can't do simple. Okay, moving on. It's number 8. It's the number 6 rock, more dense, like me. Number 7 rock, more heavy. All right, good. Yay. Number 9. Find the momentum of the object with a mass of 200 kilograms and a velocity. This is also from the last lesson. Cool. All right, fine. So momentum. I remember this one, Mom. Yep. And in this case, it's mass times velocity. So it's just mass times velocity. So mass is 200 kilograms. And velocity is 35. I'm not going to do direction, but you realize that it's there, kilometers per hour. Cool. So if you can do some simple math, you can get this one down. So at 7,000 kilograms times kilometers all over hours. There you go. That's your mom, or momentum. Number 10, I'm not going to spend much time on it. It's from the last lesson. Number 10 is another density problem. Cool. I love density problems. Good on dance. In this case, we have, so density is mass over volume. I need to write this so I don't put things in the wrong place. So density of water is 1 gram per centimeters cubed. Cool. Will an object with a density of 12... Did I put the wrong units here? Yeah, I did. Wow. I'm going to go back here quickly. It's supposed to be cubed. I should be cubed because I can't cube. All right, moving on here. Cool. Yeah, no backtracking, fixing my mistakes. It's all done in live. So again, so the density of water is 1 gram per centimeters cubed. Will an object with a density of 1.2 grams per centimeter cubed sink or float? Explain. Okay, so water is 1. Okay, so water is 1. So grams per centimeter cubed. So if the object is 1.2 grams per centimeter cubed, let's think about what that means. That means there is more mass in the same volume. So the object is more massive given the same volume. That means it's going to sink. So if you have more mass in the same volume, you are going to sink. Now, yeah, so that's the explanation. You have more mass, you have more matter, you have more particles. More particles. So more particles, essentially more stuff, more particles in the same volume, and you will sink. Yep, that's it. And number 11, it's essentially the same thing. It says the density of water is 1 gram per centimeter cubed. Will an object with a density of 0.8 grams per centimeter cubed sink or float? In this case, it will float because there is less matter than water has. So essentially you're occupying, and again, this comes to the Archimedes principle. So essentially you are lighter than the water you displace. That's the way it works. For number 10, being 1.2 grams per centimeter cubed, you are more dense than water, which means you are heavier than the water that you would displace. So, for example, let's say Alex Hensley is going to go for a swim, right? Or Tanner, or I don't know, Divi, they're going to go for a swim. I'm not sure which of you swim, but when you jump into the pool or wherever you're going to jump into, you are now going to displace water. So you are going to try to move the water out of the way. And if you are heavier than the water you're going to move out of the way, you will sink into the water. Now, we don't sink in water because we are less dense than water. That's because a lot of us is, first of all, water, but also air. Our lungs and some other parts of our body are filled with air, which is significantly less dense with air, which is why you don't want to gulp on water. As if you gulp water, you fill your lungs with water, you are suddenly more dense than water, and you will sink. So whatever you do, if you're in water, don't, gulp on water. Do not fill your lungs with water. I know, counterproductive. Probably if you're doing that, you're kind of suffocating. Yeah, don't suffocate when you're in water, or else you'll sink on top of everything else. So there you go. That was the explanation. Number 12. Do I have enough space? Maybe, barely. I'm just going to erase all. Erase all. All right, cool. So in an enclosed cylinder, ooh, yes, it's one of these problems. Cool. The Bernoulli's principle? I think it's the Bernoulli's principle problem. No, wait. Let me go back here. I want to say it's Bernoulli's principle problem here. Pascal's. No, it's Pascal's. My apologies. It is Pascal's. So this is the hydraulic cylinder. Yeah, this is Pascal's. So this is all about hydraulic cylinders. So essentially, what it says here. So an enclosed cylinder. So essentially, when it says enclosed, means there's no place for anything to leak out. Everything's closed off, so things can't leave the cylinder. So it's a sealed. That's the word I'm looking for. It's a sealed cylinder. So there is a valve with an area of 2 centimeters squared, applying pressure on a valve that is 10 centimeters squared. So you have two valves. You have a cylinder and you have two valves, and which is not uncommon. So you're going to apply a force of 250 newtons. So the way it works is in a cylinder, you can have one valve on one side of the cylinder and another valve on a different side of the cylinder. Now the valves can be the same size, or the valves can be different sizes, and this is typically what they'll do. In hydraulics, they'll have different sized valves. One valve on which you apply the pressure on, and the other valve, which is the working valve. It's going to actually do all the work by pushing on something, like an object, like, maybe a weight or a pulley system in a crane. So you have two valves here. So again, well, let me draw this since I can't. So essentially, that's a closed off cylinder. It's a cylindrical feature, and you have two valves here. So this one right here is going to be, so this valve is 2 centimeters squared in area, while this valve right here is 10 centimeters squared in area. Now what you're going to do, you're going to apply pressure on this valve right here. So you're going to apply pressure on this valve right here at 250 newtons. What happens to the larger cylinder? So now remember, according to Pascal's principle, pressure is applied equally throughout. So this pressure is going to go through this valve and equally apply on this particular valve, because the fluid can't go anywhere. So you're going to multiply your force. Now how much are you going to multiply that by? You're going to multiply that by the differential proportion of the valves. Well, the valves in this case are, one is 10, the other one is 2. So 5 times bigger. So this valve right here, the big valve, is 5x bigger than the small one. So you're going to multiply this force times 5, which is going to give you 1,250 newtons worth of force. And again, that's how hydraulics works. That's how all hydraulic systems work, including brakes in a car. That's how you're able to stop a car. Well, nowadays there's hydraulic boosted brakes, but back in the day when hydraulic boost didn't exist, that's how people were able to stop those older cars with just your foot, because it would amplify the pressure. But that's essentially the problem. That's number 12. And that's it, right? We only have 12 questions. Cool. So apologies to number 1, and yeah,